Application of Euclid's division lemma algorithm. Euclid's division lemma algorithm has several applications related to finding properties of numbers. One of the main uses of Euclid's division lemma is to find the HCF of two large numbers. The Euclidean algorithm may be used to solve Diophantine equations, such as finding numbers that satisfy multiple congruents according to the Chinese remainder theorem, to construct continued fractions, and to find accurate rational approximations to real numbers. If we observe our surroundings, we can find several algorithms working to solve our daily life problems: social media networks, GPS applications, Google search, e-commerce platforms, Netflix recommendation systems, etc. All of these applications are powered by high-performance algorithm. We give some examples of these applications below.
Example 1 show that every positive even integer is of the form 2q, and that every positive odd integer is of the form 2q plus 1, where q is some integer. Solution: let A be any positive integer and b equals 2. Then, by Euclid's algorithm, a equals 2q plus r, for some integer q is greater than or equal to 0, and r equals 0 or r equals 1, because 0 is less than or equal to r less than 2. A equals 2q, when r equals 0, a equals 2q plus 1, when r equals 1. If a is of the form 2q, then a is an even integer. Example 2 show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. Solution: let A be a positive odd integer. A equals bq plus r, where 0 is less than or equal to r less than b, given 0 is less than or equal to r less than 4, r equals 0, 1, 2 and 3. A equals 4q plus 0 equals 4, k equals 4q plus 1, or a equals 4q plus 2, or a equals 4q plus 3. As we know that 4q is divisible by 2, it is an even integer. Similarly, 4q plus 2 is also divisible by 2, it is also an even integer. Thus, 4q plus 1, 4q plus 3 are only odd integers if 0 is less than or equal to r less than 4. Example 3 show that any positive odd integer is of the form 6q plus 1, or 6q plus 3, or 6q plus 5, where q is some integer.
Solution: let A be any odd positive integer and b equals 6. Then, using Euclid's algorithm, we get A equals 6q plus r. Here r equals 0, 1, 2, 3, 4, 5, because r is greater than or equal to 0 but less than b, and b equals 6. A equals 6q plus 1. An odd number equals 6q plus 2. An even number equals 6q plus 3. An odd number equals 6q plus 4. An even number equals 6q plus 5. An odd number. So odd numbers will in form of 6q plus 1, or 6q plus 3, or 6q plus 5. Example 4: an army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? Solution: by using Euclid's division algorithm, 616 equals 32x 19 plus 8 are not equal to 0. So, again applying Euclid's division algorithm, 32 equals 8x 4 plus 0. HCF of 616, 32 is 8. So, they can march in 8 columns each. Example 5 used Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m.
Solution: let b equals 3, then 0 a currency r3, so ar equals 0 or 1 or 2, but it can't be 3 because r is smaller than 3. So the possible values of a area 3q or 3q plus 1 or 3q plus 2. We know that a equals 3q or 3q plus 1 or 3q plus 2 a 2a equals 3q 2a or 3q plus 1 2a or 3q plus 2 2a 2a equals 3q 2 or 9q 2a plus 6q plus 1 or 9q 2a plus 12q plus 4. Case I, 2a equals 3q 2a where m equals a 3q 2. Case 2, 2a equals 3q 2a plus 2q plus 1 where m equals a 3q 2a plus 2q. Case 3, 2a equals 3q 2a plus 4q plus 1 where m equals a 3q 2a plus 4q plus 1. Thus, we see that a2a is of the form 3 meters or 3 meters plus 1 where m is any positive integer. Hence, it can be said that the square of any positive integer is either of form 3 meters or 3 meters plus 1. Example 6. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9 meters plus 1 or 9 meters plus 8. Solution: let a be any positive integer and q equals 3, then a equals 3q plus r for some integer q a 0 yen and 0 a currency r3. Therefore, a equals 3q or 3q plus 1 or 3q plus 2. Case I, when a equals 3q, a cubed equals 3q 3a equals 27q3 equals 9, 3q3 equals 9 meters, where m is an integer such that m equals 3q3. Case 2, when a equals 3q plus 1, a 3a equals 3q plus 1 3, a 3a equals 27q 3a plus 27q 2a plus 9q plus 1. Example 7. A sweet seller has 420 kaju, barfis and 130 badam barfis. She wants to stack them in such a way that each stack has the same number, and they take up the least area of the tray. What is the number of that can be placed in each stack for this purpose? Solution: use Euclid's algorithm to find their HCF. 420 equals 138 tilde. 3 plus 30 130 equals 38 tilde. 4 plus 10 30 equals 10 a tilde. 3 plus 0. So, the HCF of 420 and 130 is 10. Therefore, the sweet seller can make stacks of 10 for both kinds of barfi.